In the previous videos, we saw that what Dalton represented in terms of the model of the atom, what J.J. Thomson represented, and what Rutherford represented. As we summarized at the end of the lesson, what J.J. Thomson did is that he presented that within the atom we have some more particles, and then what Rutherford model of the atom had or brought into the world of science is that he took the nucleus as a separate entity from the electrons, and then nucleus is at the center of the atom and the electrons are going around. We discussed even the anticaps or the flows that Rutherford model of the atom has, and the main thing is if the electrons are moving around, how come that those charged particles accelerating are still not emitting energy, or if they are emitting, how, and why is the model of the atom still stable? But before we proceed to discuss the Bohr's model of the atom, let's see some of the experiments and the revolutions that are done in quantum theory. Okay, so now one of the observations that was unexplained by the end of the 19th century was the spectrum of light by hot objects, which is known in the other words as the black body radiation. At normal temperature, around 300 Kelvin, we are not aware of the electromagnetic radiation because of the low intensity and long wavelength. However, as the temperature increases, there is sufficient infrared radiation that can be visibly glow. And then as the temperature increases even more at above 2000 kelvins, objects glow with a yellow or whitish color, and as the temperature increases even more, the electromagnetic radiation emitted from bodies is stronger at higher and higher frequency or smaller wavelength. The curves of light intensity versus wavelength were different for different temperature are called the blackbody radiation curves. The term blackbody was introduced by Kirchhoff. Okay, and it refers to an object that completely and perfectly absorbs any light energy that falls into it, and then perfectly re-radiates the energy as the energy of light. The energy is radiated, that is re-radiated, can be perceived from this curve, the blackbody curve, which depends only on temperature. As you see here on this picture that you have here, at the 600 6,000 Kelvin, so the curve here at the 6,000 curve, we will see, which is corresponding to the temperature of the sun, we will see the visible spectrum at the peak. Okay, the visible spectrum is here. And then as it goes down, we will have the infrared, and as it goes up or to the left, then we will have the ultraviolet radiation. The major problem that scientists were facing was to explain why is this happening. Maxwell's electromagnetic theory, which we will see it later on, has predicted that oscillating electric charges uh, produce electromagnetic waves, or charges that have acceleration produce electromagnetic wave. A thermodynamic approach also reasoned that hot objects like the filament in the light bulb emit light as a result of the vibrating atoms or charges in the filament. Since heat is manifested as a faster, more violent vibration of the atom in the object, the frequency of the radiation emitted by a hot object should increase as the temperature increases. But an application of those ideas did not work. Therefore, we can say safely that the classical physics failed to explain the relationship between the temperature and the black-body curve. And it also made a completely absurd prediction. The hot object would emit energy most effectively in short wavelengths. This prediction led to a this prediction leads to a bizarre conclusion. If you hit an object, it will emit a smaller amount of infrared energy, a little more red light energy, more blue, more violet, and a tremendous amount of X-ray, and so on. In short, hitting an object would result in an infinity amount of gamma radiation being produced. This prediction was called the ultraviolet catastrophe, and it was obviously not true. So here it comes that is known as the Planck's theory of matter. Planck was in the early 1904, I think it was. He proposed an empirical formula that nicely fits the data. And what he was saying, so by this formula, what he was saying, making this radical assumption, which enters us into more quantum theory of the matter, model of the matter, that the energy distributed among the molecular oscillators is not continuously, but it is instead has a finite number of a very small discrete amount. And then the formula that he presented is that the energy is H times F, or where H is known as the Planck's constant. Is known as the Planck's constant, and it is even in your formula sheet as 6.63 times 10 to the power of negative 34 joules times seconds. Planck's called each discrete bundle a quantum, which means a fixed amount. And in plural, it is quanta. So if we have more, then it is in a multiples of, if we have more quantums. Now, another thing that Planck represented is that light is composed by tiny bundles of energy, and each of those photons, because photon is from the Greek word of light, so each of those energies is calculated as HF. And if we have multiples of photons, then the energy of all will be calculated as n times h times f, where f is the frequency of the wavelength of the light. Sorry. Okay. For many years, Planck himself resisted to accept this. However, this was the only it's the start of that we know now as the quantum physics, and then Einstein entered into the field, and then he grabbed that information, grabbed that um, principle and brought it to explain even more phenomena, as we will see on the following video, following lesson, that it's the photoelectric effect. Now let's stand a bit at this formula. So the energy that one photon carries, just to clear this, one photon carries is h times f. From the fact that universal equation of the wave is that the product of the frequency and the wavelength is equal to the speed. This is the equation, the universal equation of the wave. Since we are dealing with light, it is accepted that the speed of light is a constant and it is equal to c. And therefore, the frequency will be equals to v over lambda. So if we have one photon, then the energy will be maybe calculated as h times f, or h times c over lambda. Both of them are right, depend on what you are looking for or what you are given to you. And if we have multiple of photons, then the energy of m photon is equal to n times h times f, or n times h times c over lambda. And again, f is the frequency, c is the speed of light, which is a constant, and lambda is the wavelength of the photon or the light. Let's see now an example in which we are calculating the energy of an infrared photon with frequency of 3.45 times 10 to the power of 14 hertz. So it is one photon, so the energy will be either HF or HC over lambda. Since what is given here is the frequency, then we will use 6.63 times 10 to the power of negative 34 joules times seconds times the frequency, that is 3.45 times 10 to the power of 14 hertz, which is nothing but 1 over seconds. So seconds and seconds will cancel out and will give us the energy of one photon as 2.29 times 10 to the power of negative 19 joules. So it is a small energy, but when it is calculated, when it is taken a lot into consideration, then it will be a considerable value. Now, if we have example 2, if we have a laser with a wavelength of 650 nanometers, and if the power of the laser is 1.5 volts, how many photons are coming out of the laser every second? Every second. Okay, now first let's calculate the energy using the power information. Now we know that power is the rate of the energy. Okay, so how much energy is produced per unit of time? E over time. And now since the time is 1 second, then we can find that the energy is equal to P times 1 second, or the energy is equal to 1.5 joules. Now that we know the energy, let's calculate the number of photons. So the energy formula will be N times H times F, or N times H times C over the wavelength. And then since we know the wavelength, we will use this formula here, and we will look for what is the number of photons that are emitting this amount of energy. So N will be equals to the energy times lambda over H times C, that is the speed of light. So 1.5 times 650 times 10 to the power of -9, that is converting the nanometers into meters. And then we have the Planck's constant as 6.63 times 10 to the power of -34 times 3.0 times 10 to the power of 8. And after we plot this in the calculator, we will find that the number of photons is 4.9 times 10 to the power of 18 photons. Now we know even from the J.J. Thomson, as well as the Millikan's oil drop experiment, that charges are quantized, and they are multiples of elementary charge, which is the charge of the electron. Okay. Now let's take a look at the different unit of energy. So we have seen joules, and this is the main, the unit that we have used up to now. But even as you notice here from the examples that we have done, is that the energy is too small. So if we consider that we have an electron that is moving into two different positions, delta V, then the energy is to the power of -19, because -19, -18. So it is very, very small for us to perceive number as to the power of -19, -18, or so on. So therefore, what we are doing now is we are presenting a different unit of energy, which is known as the electron volt, or EV. So what this is the work done on an electron to move it with 1 volt. So the energy, which is the work done on the electron to move it into 1 volt, will be calculated with charge times V between two parallel plates. So 1.60 times 10 to the power of -19 times 1 volt this is coulombs, times 1 volt, will be equals to 1.60 times 10 to the power of negative 19 joules. And what we do is we call this 1 electron volt. Okay, so instead of saying now that we have 1.60 times 10 to the power negative 19, for us is easier to perceive, to understand that we have 1 electron volt. And this is the ratio of conversion that we will use. So now, when we have joules, when we are working with units of joules, H will be 6.63 times 10 to the power of negative 34 joules times seconds. And when we are working with electron volts, that will be Planck's constant will be 4.14 times 10 to the power of negative 15 electron volts times seconds. So what you have to be careful to which units you are using or which units you need to use and express your answer. So if we have now an electron that is moving at a difference of potential energy of 2000 volts, let's say, and we are calculating the energy or the work that is done in joules, and the energy or the work that is done in electron volts, then what we will do is when we are working or when we are finding the work done on joules, then we will use Q times V, or 1.60 times 10 to the power of negative 19 times 2000, which will be equals to 3.2 times 10 to the power of negative 14 joules. But when we are using the electron volts, so this is joules and electron volts, again is Q times V, but now instead of saying 1.6 times 10 to the power of negative 19, we'll just say 1E times 2000 volts, and this will be 2000 kind of E electron volts. Okay. So let's see now another question in which we are talking or figuring out what is the wavelength of the radiation when we have the energy given in electron volts. So if the energy is, let's say, 5.0 electron volts, what is the wavelength of this photon that carries this energy? Now, the energy, or based on Planck's formula, we have H times F, since we are dealing with 1 photon, or H times C over lambda. We are looking for lambda, so we will use H times C over lambda. And then from here, lambda will be H times C over the energy. Since the energy is given in electron volt, then instead of converting the energy into joules, we use the Planck's constant that has those units, electron volts times seconds. So 4.14 times 10 to the power of negative 15 electron volts times seconds times 3.0 times 10 to the power of 8 meters per second. So seconds and seconds here are cancelled over the electron volts, which is 5. So electron volts and electron volts are cancelled. And what we are left with is meters, which is the unit for the wavelength. So the wavelength, if we convert it into nanometers, will be 249 nanometers. Okay. This was for black body radiation and for the Planck or quantization. We'll see you on the next lesson.